is, well, here's the first generation connected set, here's the top of a building, and here's the sides of a building, and then here's a courtyard that's enclosed. One of the things is, if the courtyard isn't the lowest in elevation, if it's slightly raised, then this will wind up being the last child. It'll be a last child. You'll grow the ground, and then the ground will have the wall as a child, the wall will have the roof as a child, the roof will have that wall as a child, and that wall will have the courtyard as a child. So it won't have any other children to meet that threshold. But one thing is that the average elevation of these triangles will fall below about 1.5 meters plus the floor average. So if you're a non-wall connected set and you're falling below the floor average, then we're going to wind up assuming that you're a courtyard. And then I actually was stunned to find, one of the assumptions that this algorithm makes is that buildings abruptly protrude from the ground. Sure enough, in the data set that I was working with, I guess which I had to be fortunate because the data sets that I had like thousands of buildings, and you'll have some peculiar buildings that will wind up causing, that'll wind up challenging heuristics or general formula framework that you wind up implementing. And one of which is, what happens if the building has a ramp that leads up to the roof? All right, the ramp is going to actually, the ground will grow, and the ground will grow up the ramp and on top of the roof, and the roof will be misclassified as ground. One thing you can do to combat that is you still have this wall-connected set here, and you can look at triangles adjacent to the top of that wall-connected set. Here's the wall-connected set. You can look at the highest two points within triangles that are in that wall-connected set, and you can look at triangles that are adjacent to the top of that, and you can do region growing as long as they fall above the floor average of that wall-connected set. Okay, that will work to identify buildings, but then what happens if you're at the top of a ditch? You're not really at the top of a building. And if you're at the top of the ditch, then you'll do the region growing and you'll replace all of the ground as and call that building. So what we wind up doing is when you're at the top of here and you do this region growing, make sure you don't come in contact with 50 different wall-connected sets. If you do, then chances are the building doesn't have 50 walls, and you're not at the top of the building, the side of a building that has a ramp on it. Instead, you're at the top of a ditch, and you wind up growing and coming in contact with too many buildings. So this is another heuristic that we wind up implementing to combat buildings that have ramps leading up to their roofs. There's also, I noticed, observed some other things where, what happens if you have a string of trees adjacent to the building? So you have the building, and you do the region growing scheme, and the wall-connected set will encompass all of the walls of the building. But then if there's a huge stream of trees next to it, and the point spacing in the LiDAR isn't significant enough to get returns between the ground of those trees, then the wall will bleed out to encompass all of those trees. So we wind up implementing the assumption that if you are a wall and you're belonging to a building, then the triangle in that wall has to be immediately adjacent to the building's roof. So if you have a building's roof and it has a non-wall connected set, and you have the wall connected set encompassing the side of the buildings, but then you have a wall connected set that bleeds all the way out with no non-wall connected set triangles adjacent to it, chances are those are trees next to a building. And we wind up using this assumption to eliminate that. There is a possibility you can get dense vegetation. And this is tough when you're looking at just the LiDAR data. If you're looking at just the LiDAR data and the vegetation is really dense, if it appears as like an abrupt protrusion from the terrain and you don't get any returns penetrating the canopy, then it can look a lot like a building. If your sensor is collecting first and last returns, you can take the difference between those first and last returns. And if the difference between those first and last returns is high, chances are high first and last return differences aren't going to correspond to building. Because as the laser beam comes in contact with the top of a building, it simply returns. You don't get a first and last return difference because the laser beam isn't going to penetrate the building. Whereas you will get large first and last return differences between vegetation. And if you do have large first and last return differences, you can wind up eliminating those triangles as non-building. I chose, the reason I did 4.6 meters for this to threshold triangles as being non-building, you'll actually find this is a sensor-dependent parameter. What happens is the sensor, when the laser beam returns, it says, okay, I've detected a signal, and it jumps up and says, I'm not going to take any more laser beams, I've accepted a signal. And then once the signal is registered and the time difference is taken, then the receiver latches down, and then it's able to detect the signals again. So what this means is it can only detect signals so fast. The sensor has a dead time. So If the first and last return pulses are sufficiently apart, then they've returned within a significant time difference. If they're too small, then sometimes the sensor won't be able to accept them. So this was related to the time difference in the sensor. This is a block diagram for the building detection for the pseudo homotopy trees. After we do the region growing, which I mentioned earlier, we identify the ground-connected sets with that heuristic that I talked about, where we say, hey, if you have a lot of children, you correspond to a ground. And then and then we look at the first generation connected set and we calculate that floor average I talked about. Then we identify buildings and non-buildings and enclosures. Remember, enclosures are the ones that have non-wall connected sets below the floor average. And then we wind up doing the region growing to eliminate to detect buildings where we found that they had ramps leading to their roofs. If the first and last return pulses are different or are available, we'll use that heuristic to take advantage of that. If they're not, then we'll just go straight through and use the heuristic to say, hey, do you have a sufficient amount of area? Does it have a sufficient amount of area to be considered a building? Otherwise, if it's less than that, it's non-building. And then we take care of that wall bleeding, and then the output is the building detection. We also get the ground from this heuristic, and then from some of the other heuristics, we'll get non-building as well. I wound up for my dissertation procuring, and this was the work that I did for my dissertation, I was able to get a hold of 2 data sets. One was the Fairfield data set containing about 2,200 buildings, and the other data set I'll mention in just a moment. On the left, you have the LiDAR data, which has about approximately 1 point per 1.2 meters squared point density. But again, that's irregular because the data is irregularly distributed. And in the aerial imagery, we had a 15 centimeter resolution, or 1 pixel per 15 centimeters. And then here's the Anchorage data set. The hotter the color, the higher in elevation. The colder in color, the lower in elevation. You can see that the terrain, it varies. It's a little deeper here, and then it's higher here. And here's the aerial imagery, 15 centimeters. The LiDAR data is 1 point per 1.5 meters squared. There were no first and last return pulse differences in the Anchorage data set. The Anchorage data set was provided by the render rasterized. It's like a range image. The points are regularly distributed. Whereas the Fairfield data set was provided by the vendor. It was a regular point cloud. If the points are irregularly distributed, you'll find them in the academia or the literature, and they're typically referred to as a point cloud. If they've been rasterized, then they're referred to as a digital surface model. If they've been rasterized and they contain only the ground, it's a digital terrain model. DTMs and DSMs is the acronyms they use. For my dissertation, I painstakingly manually extracted over 3,100 buildings. I wanted to be very sure that the algorithm, that if I claimed they could detect buildings, what is the algorithm's accuracy? I extracted the buildings with a software called Quick Terrain Modeler that's been released by Applied Imagery, which is the advanced physics lab. And I want to say, if you go to appliedimagery.com, you'll see the university who makes that software. And then I manually identified the buildings in the aerial imagery with Photoshop. So how do we get the accuracy for this algorithm? Well, we can evaluate it with what's called true positives, and false negatives. You have a given point set, P sub I, where there's n total of number of points, and P sub I are those points. I varies between 1 to n, and it's a set of points P. And these points can either have 2 conditions. The algorithm, as it automatically labels points as either building or a non-building, we're going to refer to that as the automatic set. As I manually labeled the buildings, that's the reference set. So if the point belongs to the reference set but not the automatic set, then that's a false negative. If the point belongs to the automatic set but not the reference set, that's a false positive. If the point belongs as building to both the automatic and the reference set, then that's a true positive. And in the industry or the academia, I've seen 2 terms that used to evaluate an algorithm's performance called completeness and correctness. Completeness is the sum of true positives all over true positives plus false negatives. Completeness is of all of the points that belong to building, how many did you classify as building? That's the completeness. Correctness says of all of the points that you've labeled as building, how many of them actually correspond to building? So, I mean, if you label all of the points in the entire data set as building, your accuracy is 100%. You've identified all of the building points. But not all of those building points necessarily correspond to building. So you'd have 100% completeness, but that would come at the cost of your correctness. You want to have both a high completeness and correctness, but you'll find maximizing the two will sometimes come at the expense of one or the other. You can also define building level completeness and correctness. Let's say you look at an entire label, a building label in the reference set. If that has sufficient coverage, or it has other labels corresponding to it in the automatic set, then that's a true positive. If that label in the reference set does not have sufficient coverage in the automatic set, it's a false negative. So if you've identified a lot of the bit labels, and your labels in the automatic set have a lot of labels in the reference set corresponding to them, then your building level completeness is higher. However, and when I say label, I mean the collection of points you've identified as a single building. That's a label. And then does that label correspond to other labels in the reference set? Again, if the label in the automatic set, if it has sufficient coverage, so here the reference set had sufficient coverage in the automatic set. Here, does the automatic set have sufficient coverage in the reference set? And then this will wind up corresponding to correctness. I've summarized these metrics here. Rottensteiner, in his paper in 2005, goes through great lengths to describing this in set theory in a couple pages, but that's the basic gist of it, is how you define building level completeness and correctness. Here's the point level completeness and correctness for the Fairfield data set is 92 and 82% respectively for the algorithm's performance, and the Anchorage is 89 and 75% completeness and then correctness. Here's a visual plot where red is good or corresponding to true positives, green is bad or corresponding to false negatives, and orange is false positives. Orange is something we've called building, but it is in fact not. Green is something we've called non-building, when it is in fact building. For the most part, your oranges are actually confined to vegetation, and then for the most part, the greens are actually the smaller buildings. The algorithm had a little bit of trouble with identifying some of the smaller buildings, and then sometimes it had trouble mistaking the ground as mistaking the vegetation as building. What you can actually do is, the algorithm is a tertiary classifier. I mentioned that it can identify ground, building, and non-building. Here's results for the Fairfield and the Anchorage data set for what is classified as building, ground, and non-building. And I only extracted the buildings to evaluate it for its building performance, but it does a really good job at identifying the ground. Here's the port where they call this portion building, but this is in fact vegetation here, and that's why it showed up as an error in the previous slide. But a lot of the time, the vegetation corresponds to orange, which is non-building. Green is the ground, and then there's what it's calling building. Here's the algorithm's accuracy as a function of the building size. So before we showed for all the points what's its performance. What is its performance for the building size? I actually joked with my committee, it almost looks like a transient response. I'm an electrical engineering PhD. It was nice to use an electrical engineering term with all this computer science that I wound up doing. But the algorithm's performance will have trouble with the smaller buildings, and here's the building area here, and then the pink line represents completeness. The dark blue line represents correctness, and you'll see the completeness and correctness get higher and higher as the building size gets greater. One thing to keep in mind, though, again, is at greater than 250 meters squared, the plots start to look at about the same, and you'll see for greater than 250 meters squared, we have a 90% correctness and a 95% completeness, and about 262 meters squared corresponds to a house. So you can see that it's able to identify the house, some of the larger houses in the industrial buildings pretty well, but it turns out the Fairfield data set, like a lot of the people that were living in that particular data set had 3 or 4 sheds. So there winds up being like quite a few sheds there. And then here is the cumulative completeness and correctness. So for all buildings having a size of greater than 30 meters squared, the correctness is 70%, the completeness is 75%. So it's cumulative completeness and correctness. This is for the Fairfield data set, and here are similar plots for the Anchorage data set. Here we have building histograms. The total size of the bar represents